Okay, so this is the last section. And the problem presented will be number 16. So now it's the, so all presenters, please write down your name on the blackboard. So let's start the preparation of the reporter. presentation from the
Good afternoon, honorable judges, opponents, and reviewers. My name is Xu Ray, and this is a report from TYPT PF5. I'm going to report problem number 16, cushion catapult. And this is the outline of my presentation. This is a problem statement. Place an object on a large cushion and drop several other objects in such a way that the first object is catapulted away. Investigate how the exit velocity depends on relevant parameters. And our main focus on this problem is the exit velocity and relevant parameters. And this is our experimental setup. And this is a demonstration video. So you can see that when we drop a baseball at the right side of the cushion, the marble on the left will fly away. And for our theory, we observe that when the baseball is dropped, it compresses the cushion. So therefore, there will be a compressed volume. And due to the compressed volume, the other parts of the cushion will have a rise in height. And we believe that the rise in height will do work on the marble. So here is how we change the compressed volume into the risen height in this equation over here. And here, A1 is the cross-sectional area of the baseball, and A cushion is the total area of the cushion. And X is the saturation of gas. We define the saturation by the amount of gas inside the cushion divided by the maximum amount of gas the cushion can hold. And after the compression of the volume, there will be a difference in the pressure on the left side and the pressure on the right side. And this is the pressure on the left. So instead of only the atmospheric pressure, after the baseball lands on the cushion, there is a pressure formed by the weight of the baseball, which is this one over here. And also, the impact force will also cause another pressure on the left, which is this one over here. And this pressure can be expressed at this equation over here. And because before the collision, the pressure on the right is going to be the atmospheric pressure. And therefore, there is a pressure difference on the left and the right. So we minus the pressure on the left and the right, and we get this equation over here. And now we want to calculate the work done on the marble with the due to the rise and height of the cushion. So this is how we calculate it. We have the pressure difference and the rise and height. And then the work done on the marble will transfer to the potential energy, which is related to the maximum height of the marble. And this is how we're going to investigate the maximum height and the relevant parameters of the marble. And because the problem statement wants us to focus on the exit velocity, but we can't really have a simple method of getting the exit velocity. So we're going to use h equals the velocity squared divided by 2 times the gravitational force to calculate the exit velocity. And we also believe that after the collision, the vibration of air molecules in the cushion will cause a standing wave, which is another factor that is going to affect the exit velocity of the marble. And this is the function of the standing wave. And by differentiating this function, we can get the velocity of the wave over here in this equation. And here, k is the wave number, and this is the definition of wave number. So we substitute the wavelength into the wave number. And also from the equation, we know that the amplitude is this one over here. And this is the observation of our experiment. So now we have the amplitude and the wave number, we can get this equation over here. And we change the velocity again into the rebound height, and it is expressed over here. And for our experiment, first we want to find the effect on the saturation of gas and on the rebound height of the marble. So this is a result of different saturations. So if the saturation is 10%, we are going to the value of x is 0.1 and 20% is 0.2, and so the maximum is 1 with 100% saturation. And from our results, we can see that there is a peak at 70% saturation, and we believe that this is the best saturation to conduct our experiment. And this corresponds to a theory of the expression of our volume. And this is a discussion of why, for bigger saturations than 70%, the ball will not have a greater height. So we believe that it is because for saturation higher than 70%, the air is too full and it is hard to compress the cushion. And for lower saturations than 70%, there is not enough air to be compressed, shown over here. And for our second experiment, we are going to control our saturation at the greatest effect, which is 70%. And now we're changing the distance between two objects to find the wavelength, to estimate the wavelength of our standing wave in our theory. And this is the result. So we choose 10 to 30 centimeters distance because for distance lower than 10 centimeters, the baseball and the marble will collide with each other, and that is not what we want to investigate. And for distance more than 30 centimeters, the marble will grow out of the cushion, and that's the limit of our measurements. So from our results, you can see that there are two peaks, one over here and one over here. And the peaks represent the antinodes of standing wave, which is the maximum height of the antinodes. And from the two antinodes over here, we can estimate the wavelength is about 24 centimeters. And this corresponds to the theory of our standing wave. And from this graph, you can see that before the first peak, the slope is very big. And there is a slight change of the slope after the first peak and also after the second peak. And we believe that it is because of the material of our cushion. So due to the material of our cushion, the wave will not have the maximum amplitude that we have in our theoretical model. So the antinode is going to be flatter, and this is why the slope is smaller for different peaks. And this is our third experiment. So we're going to change our initial release height and find the relation between this one and the rebound height. And this is our experiment. So the red line over here is our theoretical model predicted line. And here we can see that the rebound height and the initial height are positively correlated to each other. And this is a comparison to our theoretical model. So you can see that for lower initial heights, for 30 and 40 centimeters, there is a little error in these two data. There is a slightly decrease in our theoretical model. So we believe that the reason for this is because for lower initial heights, the impact time when the baseball falls down is longer. Therefore, there is more time until the marble exits the cushion. And therefore, there will be some time for the marble to slide away for the cushion. And that will affect the distance between the two objects. And we think that this is why it causes the error in lower initial heights. And this is the conclusion of our experiment. So first of all, we believe that the compression of volume and the standing wave are the important factors affecting the phenomenon of this question. And the estimation of the standing wave, the net wavelength of the standing wave is about 24 centimeters. And from our first experiment, we can see that the greatest exit velocity, also the greatest rebound height, happens when the saturation is 70%. And for lower or higher saturations than 70%, there is an insignificant effect on the volume compression. And the rebound height initial release height are positively correlated to each other. And this is the end of my report. Thank you.
So question from the opponent.
Okay, so the first question is that I want to make sure. So you only place one marble on the cushion, right?
Yes.
And you drop one baseball.
Yes.
Okay. And on page 6, you said that the volume of the cushion is constant. Right, so you assume that air is non-compressible. Is that your assumption?
No, it is compressible, but because it's compressible and the total volume is constant, so therefore we will have a rising height for the parts that are compressed.
Yes, but when it's compressed, the volume will be smaller, so it's not constant.
Yeah, the volume will be smaller for this part, but because the total volume shouldn't be changed, so the volume will be bigger for other parts that are not compressed.
Okay. Can you give me some factors that the wavelength is dependent on?
That's
What affects wavelength?
Well, I think that the position of the baseball and the marble will affect it, because it should be the antinodes of the position of the baseball.
Yeah, so just to clarify, you only measured the distance between the baseball and marble. You didn't change their position, right?
Yeah, we didn't change the position.
So
We only changed
the distance.
yeah.
Okay. So another question is, did you measure only the speed of the ball? Did you measure the direction it will fly?
Well, we measured the speed from.
Speed.
Yeah.
So you only measured the speed. You didn't measure the direction.
Well, we did, and we first focused on the rebound height.
Rebound height. Okay.
Yeah.
So you found the height. So you measured the height.
Yeah, we measured the height first.
And does the ball always go vertical?
Of course not, because of the different positions on the standing points.
Okay. Thank you.
Evaluation of the opponents. The opponent takes the floor.
So, honorable jury and fellow competitors, I am the opponent of Team Tribute, and I'm going to oppose problem 16, pushing catapult. So the problem statement is as follows, and I have marked some keywords in red, and I will discuss that with the reporter later. And I think some of the key points are the mechanism of the ball catapult and the pressure wave inside the cushion. So for the overview of the report, the reporter first used that the volume of the cushion is a constant to calculate the rise height and then the pressure wave. And he analyzed the standing wave of the cushion. For the experiment, he found the rebound height as a function of various parameters, such as the saturation, the distance between objects, and initial release height. And also, he estimated the wavelength of the standing wave in the theory. And for the conclusion, he not only investigated these effects, and he also used the standing wave theory to explain why the ball is catapulted. And I think the theory and experiment agree quantitatively. So for a few remarks to the opponent, for the reporter, there is a very clear comparison to the quantitative theory, and there are plenty of parameters discussed. However, I think there are some suggestions, so I will talk more about the problem statement later. And also, I think the reporter should provide a better view of the experimental setup. And also, I will discuss the direction of velocity, because the reporter, I assume he measured the height to calculate the initial velocity. And you may need to consider air resistance, so I would like to discuss that with the opponent. And also, the reporter said that there is a wave in the cushion. But I think maybe we should use the method to see that experimentally, and that will better prove the theory. So for a few points to be discussed, I would like to discuss the definition of some keywords in the problem statement, such as large, several objects, the first object, and most importantly, the exit velocity. And because the reporter talks about waves, I would like to discuss whether there may be disruptive interference, constructive interference, and what effect it will have on the projectile. And for the experiment, since velocity is a vector, I would like to discuss with the reporter whether all three components of exit velocity should be considered. And also, because the reporter didn't show a very clear experimental setup, I would like to discuss the methods that the reporter used to control the experiment. And also, I mentioned earlier that the reporter measured the height to derive the original initial velocity. So maybe air resistance could be some important factor, and I would like to invite the reporter. Okay, so I think let's take a look at the problem statement. So there are a few keywords here. So for example, you did place one object on the cushion, right? So here's it needs a large cushion. Why do you think it needs to be a large cushion?
Large, well,
Yeah.
how do you define large?
Yeah.
I want to ask your opinion about what large
my
means.
question. So I think large means that it is large enough so that you have a flat surface on the top. Because I think the large here, a large cushion, only if you have a large cushion, then you can control the experiment. Because, I'm not sure. Can you switch to page 19? Yes. Yes, so you said the slope is different, right?
Yeah.
Can you switch to the next page? So if the cushion is too small, this part, this part here, the curved part, I think this is the end of the cushion, right? The border of the cushion.
Is it this piece?
The border.
The border is here to here.
Yeah, so my point is, if the cushion is too small, then the effect of the border will be too significant. And I think by large, the proper writer wants us to want us to discuss the effects of the near center of the cushion. So it needs to be large. If it's too small, the effect of the border of the cushion will be too significant. And that's not the point. I think that's what large is. Yeah, do you agree?
Yeah, I agree with you, and I think that the border effects should be actually considered in our experimental error.
Yeah. Okay. So here it says to drop several other objects, right?
Yes.
But I think you only dropped one object.
Yes.
Yeah. So I think I'll discuss about that later.
Okay.
And yeah, let's discuss about the exit velocity. So you measure the height, right?
Yes.
But you also said that it doesn't eject vertically. So it does have some velocity to the side.
Yeah.
Right. Do you think the components, the velocity to the side is important?
The component on the side.
Yeah, so we have to
Horizontal.
So suppose you have a cushion and it's ejected, right? So maybe the velocity is like this. So you can compose it into B. So this is the velocity. You can decompose it into a vertical direction and a sideways direction. And you said that you did observe the ball flying sideways, right? Yeah, it did fly sideways. But if you only measure the height, you can only get this.
Yes.
Right. So do you think that will have a difference in your theory, matching with theory? Do you think that's a problem?
Our theory.
Yeah. Do you think?
Because when we do the experiment, we consider the standing waves.
Yes.
Yes, and I think that the different positions on the standing waves should be the main factor affecting the components of the horizontal and vertical one.
Yeah. So can you?
Yeah, so from our experiment, we analyzed the height because we want to find the magnitude of the vertical component.
Yeah. So your theory can only predict the vertical component. Like it only thinks that there's a vertical component, or does it also predict that there is a sideways?
Yeah, of course it will be a sideways component, but we actually don't have a certain evidence for how to calculate the the horizontal ones
Yeah, okay. So
in our standing wave theory. Yes.
So you calculate the height, right?
Yes.
And I think the formula you use is probably like something like this.
Yeah,
You use
yeah.
this.
We're not considering
But
the factors.
yeah, okay, we consider this. So can you measure the distance that it reaches? Like I'm going to tell you a way to measure this thing.
Oh, you mean the measures the velocity? Oh
Yeah.
yeah. Oh, that's we should consider that. Yeah.
Yes, you can measure it, right? Because we know it's
Because when we do our experiment, we only focus on that, and then we just get to what we didn't locate the
yeah,
point.
yeah. I think it's good if you can locate it so you can get this.
Yeah. Okay. Thank you.
Yeah. Okay. Okay. So let's take a look at other. So it says you need to drop several other objects, right?
Yes.
And you only drop one, but it's okay. So what do you think will happen if you drop several other objects?
Well, I think the problem statement said that to drop several other objects means to drop objects in different mass. I think the main focus on this term is to try to change the mass. But I think that due to our theory of the compression of volume, when we drop objects with bigger mass,
Yes.
it is obvious that there must be bigger compression of volume, right?
Yeah.
So the resulting effect will be a greater rebound height for the marble. And we think that this experiment is necessary because it's an obvious phenomenon that we can predict.
Yeah. So you think they drop several objects in the same place, or do you think they may be in different places?
Yeah, they also can be different places, but for different places, we are going to, it corresponds to our theory of standing wave.
Yeah. So let's go back. So can you please draw the standing wave where you have one object? Just one object.
Okay, so this is the motion.
Yeah.
And then the marble is over here.
Yeah.
And so if we drop, as we did, we drop a baseball, right?
Yes.
And so when we drop over here and it is compressed, this is the entangle. The position here should be the entangle.
Yes.
And we believe that this position should also be the entangle so that it will be bounce off.
Yeah.
So it will be like this, and then over time the oscillations will be like something like this.
Oh, okay. So
And there might be different numbers of nodes over here.
yeah. Okay. So let's suppose the cushion is the so let's suppose the cushion is very large, and the wave for this is still the same, right?
Yes.
Yeah. So it doesn't affect. And so suppose I drop another baseball cue. It does this.
Drop these guys here.
Yes, same time.
Yes.
So they touch it at the same time, and the wave will be like this. Suppose they are the same mass.
Like this.
Yeah. So symmetrical is so probably here and this, right? So there are two waves.
Yes.
So the first wave is like this. The second wave is like this.
Yes.
So what do you notice at the center point? Like if I drop two baseballs, is it different from the case if you drop only one?
Yes, it will be different.
Yeah, it will be different. And do you think the ball will go higher or less?
So it will be higher because it is well, because of the interference of waves.
Yeah. So it will be a constructive interference.
Yes.
And this will make the ball go higher.
Yes.
Okay. And same case, but so the wave is like this. Alright. But if I draw the baseball like somewhere here, and you make the center, this center here. So do you think that will affect, like if the ball is then dropped here?
Yes, because still according to the interference of waves,
Yeah.
the different position of the the waves will affect different types of the energy transfer of the ball.
Yeah, but what if it's a no here? Like there's no displacement, there's no pressure.
Where's the marble?
How is it here?
Oh, it's over here.
Yeah.
Okay.
So even if I add this, do you think it will change? But this
So
is
it is a null here.
Yeah.
It won't change.
yeah. So I think the point with multiple objects is to discuss this interference.
Oh, okay.
Yeah. So I think I will do this. Okay. And also, can you go to page 19 again? Yeah. Can you discuss why is the slope different?
So for the place that we, the position that we drop our baseball, this should be the biggest amplitude, right?
Yeah.
And because if we want the amplitude to be the same as this part, the surface of the cushion should be right. So it's over here.
Yeah.
So you can see that the current power series amplitude should be the same as this one, right?
Yes.
It should be like this one.
Yeah.
But because of the material of our cushion, we cannot bend it so much.
Oh.
So it will be fatter, and therefore there will be a smaller slope on the amplitude.
Okay. So you think you should consider the material of the cushion, right? So you should consider how it's elastic. You should also
Yeah, so
consider
that's this.
Yeah, that's it. Okay. So I think you mentioned the saturation of your cushion, right? Yeah, no, it's okay. I just want to say that a better way is to probably give me the air pressure.
Well, because when we do our experiment, we don't actually have any instruments to like quantify how much air pressure is.
Oh, okay. Okay. Can you briefly describe your setup because you don't really have it?
No, okay.
You have an image here. I want to see how you control your parameters. Yeah.
So here, this is the marble, this is the baseball that we release, and we have a bracket here.
Yeah.
And on the bracket, we have sort of like something to
Hold the ball.
control, to control the position of the ball.
Yeah, yeah.
And then we have a camera over here to look at the distance, and then a camera, actually another camera over here to look at the baseball is in the middle.
Oh, okay.
And then we release the ball.
Yeah. So I think you measured the distance, right? But let's suppose the baseball is here and the marble is here. The distance between them is the same.
Well, you mean the marble now on the left side and the baseball on the right
So
side?
we keep the distance between them the same, but we move them closer to the side. Do you think the bounce height will be the same?
So if we move it closer to the, well, of course it will not be the same because of the, like you said, the effect on the edge, right?
Yeah. So I think you shouldn't consider distance as a parameter. Instead, you should consider position. Right. I think you should say position because in your data you only analyze.
Well, actually, how we change our distance is we control the same position of the baseball, and then to increase our distance, we change the position of the marble.
Yeah. Okay.
So I think that's
So you fix the position of the baseball.
yeah.
Okay, the opponent start to summarize the discussion.
Okay, so first, I mentioned that there are three components of the x velocity, and the reporter said that he has observed them, and I proposed a method to measure the velocity in the sideways direction by measuring the range of the baseball. And second, we discussed the meaning of several other objects, and I think because the reporter told us that there are standing waves in the cushion, I think the meaning of several objects, dropping several objects, is that they can form a constructive or destructive interference. And later we discussed the experimental setup, and I understood more about how the opponent controls the setup. And also, we discussed the effects of the border of the cushion. And that is why quantum statement wants us to have a large cushion so that the effects of the border of the cushion can be neglected. And also, due to the discrepancy in the reported data, I think the elasticity of the cushion should be considered. Thank you.
Question from the reviewer.
For the first questions, I want to ask both of you, and what is the main characteristic of the different exit velocity and the reciprocity?
Well, so according to our theory, the main factor should be different initial heights, different saturations, and the different positions and distances of the pulse.
I agree.
Okay, and for next, and do you think that there will be a limit of exit velocity,
Limit of exit velocity.
like the next one?
Oh yeah, according to our theory, the theory for compression of the volume, the rebound, maximum rebound height and the initial height is critical.
And how about you?
Yes, because of energy conservation.
Okay, and so, and for next, and do you consider energy flow in your theoretical model as not reasonable?
Not in the theoretical model. We didn't consider any loss in our theoretical model.
Oh, okay. And next, for both of you, and what will cause the energy loss during the process?
Well, just as I said, the elasticity of the cushion might affect the energy loss, and maybe there will be turbulent flows in the cushion, and it will also have energy loss.
Yes, so the word is correct, and I would add that the friction of both the cushion and also sometimes the compression of air is not.
You mean the deformation?
Yes, yes.
Okay, okay, and for that, and the opponent you mentioned about the direction of velocity.
Yes.
And what will cause the difference of trajectory of your flying object?
The sideways velocity.
Yes, yes, yes.
Yeah, and each place the ball in different positions. The sideways velocity will be different.
Okay, and how about you?
I agree with that.
Okay, and for next, and do you think the phenomenon can be seen as a torque? Yes or no?
No, I don't think so.
How about you?
You mean at the seesaw?
Yes.
Yes.
And for next, and do you think different contact area with cushion but in same weight of the flying object will affect the result?
Yes, the cross-sectional area will be different.
I agree.
Okay, and for next, and do you think, for the reporter, and how did you make sure that the position of drop object is the same?
The position of what is
When you drop the object, and how do you?
Oh yeah, just as the opponent asked, we have a bracket to control the position of the.
And for next, and how do you think the pressure will change when the drop object hits the cushion? The pressure in the cushion.
Or according to our theory, the pressure on the left will be bigger, will increase after it drops.
Okay, and how will you?
Yeah, it will create a pressure wave.
Okay, okay, thank you. Okay, that's the end of my question.
Preparation of reviewer. review.
要不要切吗？现在是他们的。
已经切过去了。
Reviewer takes the floor.
So, hello everyone, my name is Wenju from TYPT and the topic of my review today is problem number 16, patient table. And experiments will generally focus on how does different ways of drug objects affect the disease velocity and energy conversion during the process. And for first part is about a review of the report, and in her theoretical and model, she talks about a pressure difference and the formula about the N2. And for this one, she clearly explained the theoretical model and in the theoretical model. But he didn't. The theoretical model only suit in ideal situation and didn't have accurate experiment process. And for experiment and setup, he has the initial releasing variables of initial releasing time and the gas in the volume and the volume gas of the gas and the distance of release object and the flying object. And for his problem, he clearly explained the parameters in the experiment. But she lack of parameters to connect with the theoretical model and lack of the investigation of the energy conversion, which I think is very important because that must be the energy loss during the process. And next, we didn't consider enough.
Stop. Take a break. 展现题。
等一下。
Make sure the connection is okay.
Stop. What happened?
是可能是号款的。
Now we'll start from here. Okay. So you have only minutes left.
Okay, so for the data analysis of the reporter, he has the response height and initial height, and he clearly optimized the result of each parameter, but he didn't compare them. But data error wasn't illustrated and didn't investigate the research problem statement as. And because I don't see the response height in his data chart, the problem statement X about the is velocity. And for the review of the opponents, in short question, he talked about the trajectory of flying object and the factor will affect the weight. And for his first, he clearly expressed the caution about the trajectory, but he took focus on the experiment process and didn't mention about the theory. And for discussion, he discussed about the interference in the experiments and the pressure. And he points out the error in the experiments and constructive suggestion about the error and model and expressed his own opinion, but he didn't discuss about the deductively and didn't focus on the reporter's presentation. And for the key questions, the opponent asked about which factor will affect the wavelength, and the reporter answered the position of the object. And for us, we think the different position will affect the trajectory because the direction of the force will be affected. And the opponent asked about do you analyze the missing part of the velocity, which is horizontal with the floor, and the reporter didn't do it. And for me, and I think the existing velocity should contain the horizontal and vertical direction of the existing velocity, because when the cushion hit it, the first may be contain a different direction. So I think the physics velocity should contain these two directions. And next, opponent asks about like current statement, if we drop several objects together, will the result be changed? And the reporter answer yes. And for me, I think it will also change. And as the contact area of the structure increase, and I think the physics velocity will increase. And for our case question, and I asked about the main factor of the physics velocity, and I think it's because of the weight of the dropped object. Because when the weight of the dropped object is increased, which means it contains more potential energy, so the energy they converted into kinetic energy will be also more, so physics velocity will also increase. And next, I asked, do you think there will be a limit of physics velocity? And I think yes, because the deformation of the equation will have a limit, so the physics velocity will also have a limit to gathering. And for the missing point part, and then we talk about.
This is the concluding remarks from the reporter. So first of all, according to our theory on the phenomenon, the compression of log and the standing wave are the main factors affecting this phenomenon. The rebound height is positively correlated to the initial release height according to our experimental data that our theory predict. And the greatest exit velocity happens when saturation is 70% in our experiment. And we believe that for lower or higher than saturations of 70%, there is insignificant effects on the compression of volume. And we can drop a few more objects to investigate the interference of waves. That is what we can improve, as the opponent said. And we agree with them. And we focus only on the vertical height and get the vertical component of the velocity. And also, as the opponent said, I think that we can improve by measuring the horizontal displacement and getting the horizontal component of the exit velocity. And we can also put the elasticity of the cushion into the consideration, which can cause different errors. And this is the overall concluding remark. Thank you.
So it's time for question from Julie.
Question to the reporter and opponent, since the reviewer mentioned that maybe the mass of the object you drop on question is important. Do you agree, or do you think it will affect how much?
I agree. And a higher mass would likely to produce a wave with a larger amplitude.
Any more questions? No? Okay, then now is story time for Chris. Okay, so now it's the score for the reporter. 7, 7. The score for the opponent. 7,8,977. The score for the reviewer. 77777. Okay. Any comment from jury? No? Okay, then that's the end of today's session. Thanks to everyone.